Have you ever looked at a map of the world and noticed how the continents seem to fit together like puzzle pieces? It's a fascinating observation that has intrigued curious minds for generations. The coastlines of South America and Africa, for instance, appear to align almost perfectly, as if they were once part of a larger whole. This visual similarity is not just a coincidence. If you have, you're not alone. For centuries, people have observed this curious phenomenon. Ancient map makers and explorers often pondered the possibility of a connection between these distant lands. Some even speculated that the continents might have once been joined together. This idea gave rise to the concept of a supercontinent, which we now know as Pangaea. However, it wasn't until the early 20th century that a scientist named Alfred Wegener dared to propose a revolutionary idea. The continents were not fixed in their positions, but had actually moved over millions of years. Wegener's theory of continental drift suggested that the Earth's continents were once part of a single massive landmass that gradually broke apart and drifted to their current locations. This was a groundbreaking concept that challenged the established scientific beliefs of his time. This idea, known as continental drift, shook the foundations of geology and changed the way we view our planet. It opened up new avenues of research and led to a deeper understanding of Earth's geological processes. This essay delves into the fascinating world of Alfred Wegener and his groundbreaking theory of continental drift. Wegener's work was met with skepticism and resistance, but his persistence and dedication to his research eventually paid off. We'll explore the evidence that supports his idea, such as the matching rock formations and fossils found on different continents, which provide compelling proof of their once connected past. Additionally, we'll examine the presence of glacial evidence in tropical regions, which further supports the theory of continental drift, and the challenges he faced in convincing the scientific community. Wegener's ideas were initially met with strong opposition, as many scientists were reluctant to abandon the long-held belief that continents were immovable. Join us as we unravel the mysteries of Earth's dynamic history. We'll delve into the dramatic events that shape our planet, such as volcanic eruptions and earthquakes, which are direct consequences of the movement of tectonic plates, and discover how Wegener's work paved the way for our modern understanding of plate tectonics. Today, the theory of plate tectonics is widely accepted and forms the foundation of our knowledge about Earth's geological activity. Wegener's pioneering work has had a lasting impact on the field of geology, and his legacy continues to inspire scientists around the world. Born in Berlin, Germany in 1880, Alfred Wegener was a man of diverse interests and talents. From a young age, he exhibited a keen curiosity about the natural world, which would later drive his multifaceted career. He excelled in various fields, showcasing his brilliance as a meteorologist. His work in meteorology was groundbreaking, as he developed new methods for understanding weather patterns and atmospheric phenomena. Wegener was also an accomplished astronomer, contributing valuable insights into the field. His fascination with the stars and the cosmos was evident in his early academic pursuits. Wegener initially pursued astronomy, earning a doctorate in the field in 1904. His doctoral thesis focused on the study of the atmosphere of Mars, showcasing his early interest in planetary science. However, his true passion lay in studying the Earth and its atmosphere. He was particularly interested in understanding the forces that shaped our planet and the dynamic processes at work. Wegener's adventurous spirit led him to participate in several expeditions to Greenland. These journeys were not only physically demanding, but also intellectually stimulating, as they provided him with first-hand experience of the harsh Arctic environment. These expeditions aimed to study polar air circulation, a topic of great interest in meteorology. Wegener's observations and data collection during these trips were invaluable to the scientific community. During his time in Greenland, he made significant contributions to our understanding of the Arctic climate and weather patterns. His research helped to lay the foundation for modern climate science and our understanding of polar meteorology. Beyond his scientific pursuits, Wegener was also a skilled aviator and even set a world record in 1906 for the longest continuous hot air balloon flight. This achievement demonstrated his adventurous spirit and his willingness to push the boundaries of human capability. His record-setting flight covered an impressive distance, showcasing not only his skill as a pilot, but also his determination and courage. Wegener's legacy extends beyond his individual achievements. He authored several influential books and papers that have had a lasting impact on various scientific fields. His interdisciplinary approach and innovative thinking continue to inspire scientists and explorers to this day. Today, Alfred Wegener is remembered as a pioneer who bridged multiple disciplines, leaving an indelible mark on the scientific community. His work serves as a testament to the power of curiosity and the endless possibilities that arise from a passion for discovery. Long before Wegener's time, people had noticed the striking resemblance between the coastlines of certain continents, particularly South America and Africa. It was as if these landmasses were once connected but had somehow drifted apart. This observation sparked curiosity and led to various speculations about the Earth's history. Some suggested that the continents were once linked by land bridges that had since sunk beneath the ocean. Others proposed that the Earth had expanded, causing the continents to separate. However, none of these explanations could fully account for the observed geological and fossil evidence. The mystery of the continents remained unsolved, waiting for a more comprehensive explanation. Section 4. Wegener's bold idea, continental drift. In 1912, Alfred Wegener presented his groundbreaking theory of continental drift to the scientific community. This was a time when the scientific world was dominated by the belief that the Earth's continents were immovable and had always been in their current positions. He proposed that the continents were not fixed in place but had moved horizontally across the Earth's surface over millions of years. This movement, he suggested, was responsible for the current configuration of continents and oceans. This idea challenged the prevailing view of a static Earth and revolutionized our understanding of geology. Wegener's theory was initially met with skepticism and even ridicule, as it contradicted the established scientific consensus of the time. Wegener argued that the continents were once united in a single, massive supercontinent he named Pangaea, which means all lands in Greek. This supercontinent, according to Wegener, existed during the late Paleozoic and early Mesozoic eras. Pangaea was surrounded by a vast ocean called Panthalassa, which covered the rest of the Earth's surface. This ocean played a crucial role in the distribution of marine life and climatic patterns during that time. He suggested that Pangaea began to break apart around 200 million years ago, during the early Jurassic period. This breakup initiated the gradual movement of the continents to their current positions. The continents slowly drifted to their present positions over millions of years, driven by forces that were not fully understood at the time. Wegener's theory laid the groundwork for the later development of plate tectonics. This elegant theory provided a simple yet powerful explanation for the observed fit of the continents and other geological phenomena. For example, the matching coastlines of South America and Africa, as well as the distribution of fossils and rock formations, could be explained by the movement of continents. Wegener's ideas eventually gained acceptance and transformed our understanding of Earth's dynamic nature. Section 5. Pangaea, the supercontinent. Imagine a time when all the continents we know today were joined together in a single gigantic landmass. This was Pangaea, a supercontinent that existed approximately 335 to 175 million years ago. The name Pangaea comes from the Greek words pan, meaning all, and Gaia, meaning earth. Pangaea was surrounded by a vast global ocean called Panthalassa, which covered the rest of the Earth's surface. The existence of Pangaea had a profound impact on life on Earth, as it allowed for the free movement and interaction of species across a single landmass. The breakup of Pangaea led to the isolation of different populations, driving the evolution of new species and shaping the biodiversity we see today. Section 6. Breaking up is hard to do. The separation of Pangaea, the breakup of Pangaea, was a gradual process that occurred in stages, much like cracks forming and spreading in a melting glacier. Around 200 million years ago, Pangaea began to rift or split apart along what is now the mid-Atlantic ridge. This rift marked the birth of the Atlantic Ocean. As the continents drifted apart, new ocean basins formed between them, while other areas collided, pushing up mountain ranges. The separation of Pangaea also had a significant impact on Earth's climate, ocean currents, and the evolution of life. Different landmasses experienced varying climates as they drifted to new latitudes, leading to the development of unique ecosystems. Section 7. The drifting continues, formation of oceans and mountains. The process of continental drift didn't stop with the breakup of Pangaea. The continents have continued to move and reshape the Earth's surface over millions of years. The Atlantic Ocean has continued to widen as North and South America drift westward, while the Pacific Ocean has shrunk as the Pacific Plate subducts or slides beneath the surrounding plates. The collision of continents has also played a major role in shaping Earth's topography. The Himalayan mountains, for example, were formed by the ongoing collision of the Indian and Eurasian plates. This collision, which began around 50 million years ago, continues to this day, pushing the Himalayas higher by a few millimeters each year.